Okay, let's start. Random vectors. Today we are going to study multivariate probability models and specifically random vectors. Here is the outline of the presentation of the course. We'll begin with multivariate probability models. This is a continuation of the subject of the previous week from chapter 6. So this is from chapter 5, sorry. And these are from chapter 8 of the textbook. Mainly we'll be studying vectors, random vectors, independency, and how to define expected value, correlation, covariance, and Gaussian vectors. Okay, here we have several definitions, as you can see. Multivariate CDF, multivariate joint PMF, multivariate joint PDF, and several theorems. All are simply extension of the previous lesson, where we considered bivariate variables. Now we extend to n random variables. Okay, so more than 2. All formula here will be applicable to vectors too in the next slides. As you can see, we are talking about joint CDF, which is very similar to the joint CDF of 2 random variables, joint PMF, joint PDF, and the properties of those functions given in terms of some theorems in here. Here we have an example. As you can see, here we are given a random variable, joint PDF, where we got, let's see this, I'm sorry, where we got 4 random variables. So 4 random variables here. So multiple random variable. Here we're asked to find marginal PDFs of Y1 and Y4 and Y3 and Y4. Okay. From the previous slide, you can see the theorems. You can see how to write a joint PDF of Y and Y1 and Y4 and Y2 and Y3. Sorry, this is Y3. I'm sorry. Y2 and 3. Okay, the formula is simple. To find the joint PDF of Y4 and Y1, we should integrate the joint PDF of Y1 to Y4 with respect to Y2 and Y3. So to find Y1 and Y4, we have to integrate it over Y2 and Y3. Now the limits of this integration is critical. As you can see here, the limits of Y2 is Y1 to 1. So Y2 equals Y1 to 1. And Y3 is from 0 to y4. So 0 to y4. So we evaluate this integration and find joint PDF of y1 and y4. Similarly, we can try for y2 and y3, right? Where we got again double integral fy 1 to y4. Now this should be with respect to y1 and y4. And the limits of those random variables are already given in the general joint CDF. So we can easily determine this. If we want to find the marginal PDF of any of the random variable here, for example, y3, I'm sorry, y3, then there should be triple integration, right? The same function. And dy1, dy2, and dy4. And the limits of y1, y2, and y4 again should be determined from here. You see, once a joint PDF is given for any number of random variables, we can easily find the joint PDF or marginal PDF of any random variable. Here we see two definitions: independency for random variables of x1 to xn. The independent random variables can be defined such that the joint PMF should be equal to the multiplication of marginal PMFs for discrete random variables. For continuous random variables, joint PDF should be equal to the multiplication of marginal PDFs. That's quite easy as a formula, but that's not that easy to prove it or to show this for any group of random variables. I have to try every marginal PDF, find every marginal PDF and multiply them and show whether they are equivalent or not. Independent and identically distributed. Here, identically distributed means the PDFs are identical, okay? So the PDF of the first random variable should have the same form of the second random variable and the third and then nth random variable. Then that's identically distributed. Since this equality holds, then these are independent. If their distributions are the same, then this series of random variables is called IID process, independent and identically distributed. Here we have an example similar to the previous one. As you see, we got a sequence of random variables here, and their joint PDF is given here. We have n random variables, and the range of each is from 0 to 1. Okay, and joint PDF is unity 1. Now, we define an event A, which says the maximum xi, so any random variable, should be less than or equal to 1/2. Okay, that's the event. Okay, so we have to then, now the question asks about the probability of A. Probability of A from the theorem, as you can see here, when it is discrete, that's a summation. When it is continuous, that's an integration. We simply integrate joint PDF, okay, over the range of A, okay. Now then PA, now we can define PA, probability that the maximum IXI less than or equal to 1 over 2. This requires that every X here should be less than or equal to 1, okay. Then that's union of all these probabilities. So x1 should be less than or equal to 1, x2 should be less than or equal to 1 over 2, sorry, x3 is less than or equal to 1 over 2, and xn less than, sorry, yeah, less than or equal to 1 over 2. Okay, all should be um, proved that they are less than 1 over 2. This requires simply this integration. Okay, we can simply integrate the joint PDF over the range from 0 to 1. 0 to 1 over 2, sorry. 0 to 1 over 2. And why? Because remember the formula, probability that x is less than or equal to x was simply its integration of PDF, right, from 0 to x. This was the formula. So we simply use this for joint PDF. Now, in order to evaluate this, that's 1. So 1 is simple. That's 0 to 1, so 1 over 2. Then every integral here will give us 1 over 2. Since I have n integral, then the result will be 1 over 2 to the power n. Okay, that's quite easy. And if the number of random variables here increases, then so the n increase, then the maximum probability will go to 0. Okay. Okay, now here we have random vectors. In previous slides, we studied multivariate random variables, so multiple random variables. Now we define vectors. Here is how we define random vectors. It is x, simply x, x1, xn. So n-dimensional vector. By the way, there are two ways to represent a vector in literature, two conventions. One is to use a bold letter, just like this. X is bold here, as you see, which refers to a vector. Or alternatively, we can use bar, okay, x bar. So x bar corresponds to bold x, simply, which refers to vector. We simply extend the previous analysis, multivariate probability model here, and define vectors. There is nothing different from the previous definitions. Here, we simply write a sequence of random variables as a vector. Okay, so each of this here, x1 is a random variable, and xn is a random variable. So when we put them all together in a vector, then this becomes, x becomes random vector. And as in a multivariate probability model, we can define joint CDF, joint PMF, joint PDF for random vectors. We use symbols, as you see here. So capital F refers to the joint CDF, where x is a vector, so we use a bar here, okay? Or F X. Again, this is PDF, joint PDF. So joint CDF, joint PDF, and also we define joint PNF, again vectors, so bar. Okay, so all are valid here. And we have an example here. Here we are given a joint PDF, fx of x, x is a vector. Here then we got 6 times e to the minus a vector again, transpose, right? X, another vector. Here, A simply given as 1, 2, 3. From vector algebra, we can write this 1, 2, 3 transpose, right? Similarly, we can write X. X is a random vector again. X1, X2, and X3. Or X1, X2, X3. Okay. We take simply its transpose and write in this A form. Okay, now the question is CDF of X. How to find CDF of X? We remember that the CDF, right? So the CDF, it was an integration of PDF. When this is a vector, then that's going to be a vector too. Okay, so we have to take this integration according to the number of the elements of the vector. Here we have 3 elements, so n is simply 3, so we have triple integration. So we integrate this simply 3 times with respect to x1, x2, and x3. And we can write, as you can see here, multiplication of A transpose X will be simply, so here is the A, 1, 2, 3, times x1, x2, x3, right? I'm sorry, this is inverse. Okay, so A transpose is 1, 2, 3. I'm sure that's correct, right? As A transpose. So that's going to be, okay, let's write A is that, then it's going to be, okay, first 1, 2, 3, and x1, x2, x3. So this multiplication will give us this one. Okay, minus. There's a minus in front of this multiplication. So here is my explicit expression of joint PDF. Now I have to integrate this 3 times, right? 1 for x1, 1 for x2, and 1 for x3. And here you see we got e to the minus x1. It's, I'm sorry, this integration with respect to x1 from 0 to infinity. Okay, so you evaluate this integration and you will find this one. You do it for this one, and you got this one with a factor 1 over 2 here, and this one from this 1 over 3, And since there is a 6 here, 6 is 2 times 3, so they cancel out. So we got that one. Okay, independent random variables and random vectors. Independency, as we have already described, the joint PDF or PMF should be equal to the multiplication of marginal PDFs or PMFs. And here we have an example. Again, I got the random variables, list of random variables from y1 to y4. This can be written as a vector, right? If you want, for example, y vector could be, right, y1, y2, y3, and y4. Okay, here's my vector. And its transpose could be written as y1, y2, y3, and y4. Now I can define different vectors or subvectors from this. Here it's defined. V vector is given as y1, y4 transpose. And the W vector, random vector, is defined as y2 and y3 transpose. Okay. So are V and W independent random vectors? To prove it, we have to simply write this, right? V, W vector should be equal to F, V times F, W. Okay? If it holds, then these two random vectors are independent. Now, in order to prove this, we have to find joint PDF of F V vector and W. Okay, we can also write this as this form as a vector. That's the same. There is no difference between these two random two representations. Now we define V and W, and now we have to determine this joint PDF and this joint PDF. To find this joint PDF, we have to integrate this, right, over the range of F, so the Y2 and Y3. So this is going to be equivalent to integration of F V U W D Y2 and dy3. Okay, and for this one, we have to integrate again F V W the integration here, I'm sorry, dy1 and dy1 and dy4. Okay, so when we integrate this, we simply get joint CDF of V and joint CDF of W, and the multiplication can be found here. And then since the multiplication of this two, so this one, is not equal to this one, then W and V, the random vectors W and V, are not independent. Okay, here we have some theorems. I will skip them. You can study this simply, and these are just extension of previous theorems that we have studied so far. So here the examples, definitions and examples. We have expected value vector as we define a random vector. Then we define some other functions, expected value vector. So that's going to be a vector here. So mu x bar, which is expectation of each random variable inside the vector. So expectation of x1, expectation of x2, and xn. Now, what are the components of x? So x vector, x transpose. So that's a multiplication, simply a vector matrix algebra. So we multiply this with this one, so we construct this. We multiply this with this one and construct this. We multiply this with this one and construct this. So we got here, it's 3 times 1. This is 1 times 3, and the result is going to be 3 times 3 vector matrix. Okay? These are linear algebra, matrix algebra again. Now we can define vector covariance. Vector covariance is just the covariance that we have already described. So we simply, where is that? Okay. The vector covariance is given as this formula. So here x is a vector and mu x is a vector too. You see, this is just like the covariance. You remember the covariance was x minus mu x times x minus mu x, right? So now this is the vector form. Here an example is we have an x with components, and the covariance matrix of this is going to be this one, simply the variance, as you see, of x1 and x2 and x3 makes the diagonal elements of this covariance, vector covariance. And the covariance of x1, x2, x1, x3 all are the elements of this covariance, vector covariance. We can define expected value of a random matrix as we defined here. This is very similar to this one. We can define vector correlation as previously we defined correlation. Now it was R, X, Y. Now we simply R, X vector, okay? Which is expectation of X times X transpose. So the expectation of this one actually, okay? Expectation of this one. Remember that expectation of x minus mu x squared was variance of x. Okay, so we use it in here and write the vector correlation in this example as this: expectation of x1 squared, expectation of x1, x2, x1, x3, x2, x1. So all the variations of this random variables. This is 3 by 3 vector, as we have 3 elements in the random vector. And we might remember correlation here. Correlation was expectation of x1 and x2, so we can replace these elements here, symbols, by correlations in here. And if the mean value is 0 for all these elements, then this is going to be the variance. This is going to be the variance of the second and the third element. Okay? We can also write vector covariance in terms of vector correlation and expected value of a so expected value vector, okay, in vector form. Here is an example. Here the joint PDF is given, and the expected value correlation matrix and covariance matrix, two-dimensional, of course, should be determined in here. Here is the joint PDF, sorry. As you can see, we always start with joint PDF. So if the joint PDF is known, then we can calculate all other parameters. If it is not known, then it's quite difficult to estimate, to calculate other parameters. Now, here, since this is two-dimensional, so n is 2, we can determine two expected values, and then we form the expected value vector. So here is the expected value vector. How to determine this? We simply integrate. We use double integration to find n of the expected value here. For example, for 1, for n1, then expectation of x1 is going to be integration of 2 times x1 dx1 dx2. Okay, remember the expectation operator, it was simply this. Okay, this was the formula, so we use this formula in here. That's it. Here it is 2, so 2 times x, 2x1 dx1 dx2. We just write x2 here and x2 here, and then integrate it again. The range of the integrations is important here. Note that the range of x1 is 0 to x2, while for x2 it's x1 to 1. So the limits of the integration will be determined according to the range of the random variables here. So we simply create the expected value vector. In next, correlation matrix. Remember the correlation matrix in previous slide. The correlation matrix was this. Okay. So we use it. We need to find the expected value of x1 squared, which is very well known from variance. Expectation of x squared was integration of x squared fx of x dx. This was the formula from previous chapters, previous lessons. So we adopted in here. Okay. For x1 and x2, similar. x1 and x2, x1, x2 times the joint PDF. Here we always use joint PDF instead of marginal PDF in here. So it's quite, you see, straightforward. We need mathematical calculations to find the correlation matrix. And as you see, the correlation matrix is found as 2 by 2 matrix as expected. And then the covariance matrix can be calculated by using this correlation matrix and expected value vectors. That's matrix algebra. There's nothing complicated here. Now, as we describe vector correlation and vector covariance, we can define vector cross correlation and vector cross covariance. So in previous slides, in vector correlation, we take R, X only. So we got one random vector. Now we got two random vectors, X and Y. Okay? And would like to look at their relationship. We'd like to define a relationship between them, and it's based on the use of vector cross covariance, vector cross correlation, and these are very similar to the previous analysis, except that instead of x here, for example, x transpose, now we got x y transpose. That's it. Similarly, cx, it was cx, now we got cxy. Okay? There is no big difference. The operations or calculations are very similar. Now let's see Gaussian random vector. Gaussian random vector is a vector whose components are Gaussian random variables. So we simply take an x again, whose elements is simply x1, x2, and xn transpose. And all xn are Gaussian. Okay, each with a mean value of, I'm sorry, with a mean value of, let's say, mu1, and the standard deviation sigma 1, mu2, sigma 2 goes like this. Okay, so we form a Gaussian random vector. Now its joint PDF should be somehow given in terms of covariance vector and the expected value vector. And you can see here the covariance vector, expected value vector. Here we can write joint CDF. Here, by the way, we got determinant CX, which is, you know, from the matrix algebra, how to calculate determinant of a vector. Now, suppose that given uh, we are given a random vector y, okay, which is a linear function of x, okay. So can we estimate the properties, the functions or characterization of y using A? Yeah, we can. Using this formula, this theorem, we can uh, find the expected value vector, correlation vector, and covariance vector covariance using this formula. Similarly, we can define the correlation, cross correlation, vector cross correlation, and vector cross covariance. Here we have an example. We are given sorry. Okay, here we are given okay, we are given expected, okay, we are given expected value vector, the correlation, vector correlation and vector covariance of random vector x from the previous example, A and B, and find the correlation, expected value, and the covariance vectors. We simply use the formula in this theorem to find the matrices in here. Next example, we have a linear operation. We got a linear function of x as a new random vector, and we find the cross correlation matrix Rxy and cross covariance matrix Cxy. Again, we use the same method in previous slide. Use the theorem 8-9 to find the cross correlation matrix and cross covariance matrix. Here the correlation between the elements of the vectors can be found by using the theorems that we have already studied in previous slides. Okay, Gaussian random vectors. We can use the formula in previous slide to write the joint PDF of Gaussian random vector x. Here there are two vectors that are important. One is the covariance vector covariance, and expected value vector. Once we know them, we can easily write the joint PDF. And here we get an example. We are given temperature at a certain weather station on a specific day. All are given in units of degrees Fahrenheit. taken at 3 times in a day, and they are found to be Gaussian. So Gaussian random variables x1, x2, x3 with variances of 60 degrees in Fahrenheit, of course. The expected values are given again in the covariance matrix of the three measurements are also given. Now the question is about joint PDF of x1 to x2 using the algebraic notation in previous slide. So this was the algebraic notation, and this is the vector notation. So we'd like to write the joint PDF of x1 and x2 using algebraic notation and vector notation. It's not, you see, it's quite straightforward. All parameters are given. We need to find the correlation, as we have correlation here. We have to find it. We find the correlation here using the covariance matrix. Remember that the covariance matrix here is it's 3 by 3, and each element shows the covariance between the elements between the random variables x1, x2, and x3. Okay, so we can find the correlation directly from this matrix. And using this formula, then we insert correlation into here and find it. This is the explicit form of the joint PDF. We can alternatively write the vector, we can use vector representation. To find the vector representation for 1, 2, we simply take this part only. Okay, look at here. This is 1, 2. So 2 by 2 vector. Using this, we can write joint PDF by using vector notation, as you can see here. Here we have to determine determinant of the covariance matrix and then insert it into here to get the joint PDF. Okay. So this is the last slide. Here, standard normal random vector is defined. It's expected, I'm sorry. Its expected value vector is 0, and its covariance vector is unity vector. Here, by the way, unity vector here. It's diagonal. Its diagonal elements are unity and all others are 0. For example, this. Okay, this is a unity vector. For any Gaussian random vector, we can define z as given in here. And we can write any random vector again as a linear combination of another random vector. All formula given here, and we get an example. So I think there's nothing difficult here. So you can easily apply this by using linear algebra. So I want to stop here. I think there is no question. So thank you.